Thanks, Mr. Chairman. So this presentation is about a French collaborative project gathering different research institutions and so it is about isolation building insulation renovation. Okay, so we're speaking about retrofit old buildings. And myself, I am in the engineering, industrial engineering side of the project, and with people who are more relevant to computer science and people from construction, we are trying to put and to set up a global software in order to assist that. So this has been funded by ANR, which is a national French research agency. And here you have different persons working in this different institution. Myself, I belong to this one. So, overview. First, we will quickly go through the goal of the project, and in order to identify the contributions that will be presented here. Then we will see we'll have 3 contributions. One is a process identification. Then we will provide some modeling for different facades for the buildings. And finally, an algorithm in order to design the layout of the insulation solution. And finally, we will have a short discussion and conclusion. Goal of the work. So according to European Commission, so this report is 2020, today in Europe, around 75% of building stock is energy inefficient. So we have already spoken of that in the previous presentation. This means that much of the energy used is waste. This loss of energy can be minimized by improving existing building. Because if we wait new construction, it's going to take 100 years. So it has been proved that renovation of existing building could reduce, so figures are quite important, the EU, so Europe, total energy consumption around 5 or 6%. So total energy, it's really huge. And carbon dioxide emission around 5%. So our goal, so the goal of the whole project, ISOBIM, to develop software tool to support energy efficient building renovation using prefabricated isolating panel. This means that all this is achieved off-site, and we want to minimize on-site work. Okay. So the objective and the 3 contributions. So basically, some works has been published with a building information model for retrofit. This is one I've been working on. It was almost 10 years ago. And basically, you have 5 steps. So the first one is to collect the geometry of the building. Then here you analyze the building geometry you get. And then you can design the solution for renovation. After that, off-site, you manufacture components. And then, of course, last step, you assemble this on the building. So basically, at the present time, many of this insulation work in Europe is done manually on site. And the idea is to industrialize it. So 5 main activities. Our objective, basically these 2 steps, and mainly step 3, but we need a little bit to work on step 2, which is analyzing a little bit the geometry of the building. So the 3 contributions are layout design process, facade models, and an algorithm in order to assist design. So about the layout process, so why 4 steps? So this has been achieved with talk with various stakeholders of the project and mainly architects and constructors. So the first one is to prepare the facade the first one provided by geometry, the analyzed geometry, and we get some kind of a geometric model. And the idea is to simplify the facade in order to get something that can be automated process. So we want to transform the facade in rectangular, three kinds of rectangles. What we call out-in zone should be integrated in a panel. Out-out, this should be bypassed by panel. And of course, you have support line in order to attach the panel to the facade. Yes, I've been quite quick here. I want to go back. Yeah. This is an example of what we call a panel. It's manufacture off-site, okay, then assemble on-site. So first thing, just to simplify the geometry. Then you need to make some manual design of panel because everything can't be automatized, okay? So as a second step, architect or people in charge of the design manually design the panel. Then after, you can turn to algorithm in order to automate panel design. So this is the third step. So dimension and position all panels to cover the whole facade. Optimize the building performance. Of course, the idea is to have a better efficiency. And so the simple thing is to design panel as large as possible. And finally, once this is done, so you have all your facade which has been covered with panel, most of the time architects say, oh, this is not good, you should correct this and this. So there is a manual retouching solution in order to make some modification or adjustment. So our objective is to propose better algorithm for step 3 and also propose ideas for the other steps. So this is the process. As we say, you have the renovation beam, facade road geometry, panel technology. We prepare manual design, automatic design, and manual touch-up. Okay. This process is using 3 models. So raw facade geometry, that's going to be insulated, facade ready for design, and result solution, insulated facade. So what about the facade models? So this is what we call UML class model, so Unified Modeling Language Model, just to show you the entities. So a building is a set of facade, rectangular, with elements, and elements have been categorized in non-resisting elements, windows, doors, resisting elements, floor end, cross wall, crossing of floor end, cross wall, singularities. There are many singularities in buildings. For example, air condition, balcony, garage door, pipes, lights, everywhere that you can see on the building. And something that you should add to facade that can be processed automatically. Non-rectangular element in a facade, what we call a criterion, sub-basement. There are specific parts of the facade that cannot be automatically processed. So these should be manually processed. So this is the input. And so when we prepare, we want to remove all this and keep the 3 previous elements. So once it's prepared, we have, as we said before, out-in to be integrated in a single panel, support line for panel edges, and out-out to be bypassed by panel. So this is problems that we will consider after. The result, the building is a set facade as before, and after is a set of panel. Position, 8 width, outline position, because we have windows, we have doors in the panels, and mechanical supports. Whoops. And mechanical supports in order to attach the panel to the facade. So now about layout algorithm. So in fact, layout algorithm in this situation is a quite hard problem. It's a mix between a cutting and packing problem. So there is a reference here. Many people have been working on this one. And also what is called product configuration. How to design product with a predefined set of components. The idea is you have small objects, panels, and large object, facade. And you should put the small object in the large object. But, whoops. But the dimensions of small objects are variable and must be determined. This means that you can have different sizes, okay? The quantity of small objects is variable and must be determined. This means that you have many, many variables. You have the size of the panels, position, and quantity. In cutting and packing, very often, all the sizes are predetermined and known, or the number of objects is known, okay? And so especially this quantity of small objects that is non-fixed is a problem for optimization because you don't know at the beginning the size of the problem. Is it going to be 20, 80, 40 variables? You don't know. Plus, many geometric and constructional constraints are present. Because, for example, a window should have a certain distance inside the panel for rigidity and many constraints like that. Things are explained in the paper. So it's not an easy problem. Consequence, we were obliged to investigate two kinds of solutions. A robust one, because companies are waiting for an algorithm, and us, in terms of a scientific research interest, we were much more interested in a constraints-based solution. So anyway, we have to do it. So we define a kind of greedy heuristic, we are going to see just after, to ensure a solution in a reasonable amount of time, at least less than 5 minutes. Because projects with companies counting on a robust solution, as I said. And use of constraint-based solver, why? Because for flexibility, because when you design a layout, you always have specific constraint. And in some situation, you want to add constraint or erase constraint. And so constraint-based approach would be very interesting for flexibility in programming or defining the problem. And also, constraint-based approach are very interesting in terms of optimization. If you change your criterion, constraint-based approach are very flexible. So that's why we have been investigating these two. So first, we will speak about the greedy heuristic. So goal, panels as large as possible. So basically, it's for have a better energy efficiency. But we have max dimension because this panel should be transported with trucks. And so maximum dimension is more or less in Europe, this size. Settings. So preferred panels can be either horizontal, most of the time they are going to be horizontal. In some situations, they will be vertical. And you fill the panel, you start on the left or on the right. So you begin this way or this way. And architects say, we go from the bottom to the top. We never tried from the top to the bottom. So we have two parameters, either preference horizontal or vertical, and from left to right or right to left, okay? The operating ID, mainly based on the architecture common sense, who is usually designing the solution. You identify all the points where you can start the panels. Most of them are corners in the facade. And you arrange points, the lowest right or lowest left, and you order them in a stack. Then you take the first point of the stack, and you try to take and as I say, pull the longest panels as possible. When you have the longest panels as possible, you check the geometry constraint, position, dimension, because of windows, doors, support line with, in order to have a support for the panel on the facade. Then we check the strength, constraint, and quantity, and we place the mechanical supports. So each time we design one panel, we check geometry, and we check, good, thanks. And we check the geometry, and then we check the strength. Oops. What? If panel okay, the panel is supposed to be fine. And so we remove the point and we create new starting point from new panels. So this is why it's called greedy, because we push one panel and after when it's done, we don't modify the decision and we start after for the next panel. Just in order to have an idea. So this is an example. It's a facade for a building. It's written in a mountain resort because this is a mountain here. It's going up. So here you have support lines or this kind of dotted lines. This is a door. It's an outing. It should be inside the panel. You have windows. You have balcony plus windows. So they are gathered in a single, as we said, outing. And what else? Here there is a garage door. So we should bypass this panel. So this is an example of a facade. So we're going to see an example of results. So here the setting for algorithm was horizontal and go left to right. So this means that we start here and we take the longest panel as possible. So the corner of the panel are circled just to easy the legibility of the figure. Normally, of course, there are corners. So this is the first panels. And then after jump here, put the second one. And here, it doesn't succeed to make an horizontal one here. So as there is no solution, it changed to vertical one. Place the vertical one, then an horizontal one again, and an horizontal one again. And after it's going so, okay? So basically we have 22 horizontal panels and 12 verticals. So I didn't show the support on the, but there are supports everywhere for the panels. In conclusion, so contribution. As we said, a 4-step panel design process we have seen. First, preparation, manual layout, automatic layout, and after retouch modification. 3 facade models corresponding to the key stage of the design process. We have seen an input geometry, prepared geometry, and solution. A greedy panel layout design heuristic. No constraint base. We'll see how we'll talk about that later. All integrated into a software module that will be available on the web. The software model, it's basic heuristic, so it works well and generally meets user expectation. Generally, because in some situation, users say, we would have preferred, okay. And so, as I say, they would have preferred, and we have new heuristic needs, because when you show the people how it's working like this, why can't we do something different? Okay. So new heuristic needs emerge, and what about if we do this or if we do that? But globally, this is it's robust. There is no big issue in terms of scientific. But. The constraint-based approach, we used a Shoko solver tool, which is quite famous in the constraint world, failed to produce a robust solution. Even with a good level of constraint programming skill in the projects, we were having really 2 guys that were quite good in constraint programming. Even in not so big case, in fact, you could find small cases, a little bit special, I agree. The backtrack can't find a solution quickly. This means that you begin to design a panel and then it's impossible. And then you have to backtrack, meaning to reconsider previous decision. And the problem is to find the good variables that you need to reconsider. And this is the tricky point. We need to find a way to guide backtracking to good variables. And it's very delicate because sometimes you have to put a panel, and this is impossible because of this panel here. And so it's really hard to identify which panel is at the origin of the problem. And furthermore, as we are going to see huge set of possible values, the solution space is quite big. So it seems that constraint-based approach, as I say, with discrete and non-digital variable, very fine. You have many, very good work with discrete problem. With discrete one-dimension digital, for example, task planning. When you plan tasks with constraint-based approach, you have one dimension time, okay? But here, with 2D digital as facade, if you take a facade, 20 meters, 12 meters, people want an accuracy of a millimeter. So the solution space for a facade is something like that. 240 million millimeters square. So this means that you have a huge solution space. And so maybe not so good for that. The solution space seems really too high. So I say, stay tuned. We are trying to find, because there might be ways to reduce the solution space. And I think that this is the end of my talk. So if you have any question.